in the Department of Math and Stats. And it just so happens that I am this semester teaching a course called Mathematical Modeling with Dynamical Systems. And one of the main topics that you cover in a class with that title is epidemic models. So this is something that I have known about for a while. I did a postdoc at the Mathematical Biosciences Institute at Ohio State, where a number of people, a number of my fellow postdocs were doing epidemic models. I myself have not actually published any of these, but I've been working with them in some form or another all the way since grad school, and I won't tell you how long ago that was. So I find these models really, really great, really fascinating for a number of reasons. One of which is they're extremely adaptable. Something I tell my students is that you can use an epidemic model to model the spread of basically anything. I'm getting a little bit ahead of myself here, but what we're going to talk about today is going to have a pretty general sense to it, as well as looking at some more specifics of epidemic models. So my goals for this thing, first of all, as I mentioned, I hope you think of it as fairly interactive. Please do use that Q&A. If you're not sure how to use it, you should see at the bottom of your screen a bar that says mute, stop video, participants, Q&A, and so on. So if you just click that Q&A, you should have that there. There's also a chat button if you want to do some chatting, although as Nate mentioned, we have that disabled for now. All right. So here's my goals. I want to do a brief overview of what a mathematical model is. There's sort of some key words here that I've highlighted in pink for that. So we'll talk about what empirical models are versus mechanistic. And then, of course, you may remember from math class, variables. And then models have another kind of object in them called parameters too. So I'm going to introduce those four terms. Then I'm going to start talking about epidemic models specifically. And in particular, I'm going to focus on what's called the SIR framework, which I'll talk about. And finally, we can look more closely at how you use an epidemic model. And I've actually taken some time to familiarize myself with two of the models that you may have seen in the news recently. So that would be the IHME model and the University of Minnesota School of Public Health model that's being used in conjunction with the Minnesota Department of Public Health to help the governor and other policymakers actually decide how to respond to the crisis. So if you have any questions about those specific models, then at the end of the stuff I've prepared here, we can absolutely talk about that as well. All right. Right, let's start answering some questions. So the first question I want to answer is, what is a model? What is a model? So a model is a description of something, and it uses mathematical tools. You know some mathematical tools like algebra. You might know some calculus, depending on how many years of math you took. You might even know some differential equations. So those are the kinds of tools that are used in epidemic models. But there are also statistical tools that are used in similar models as well. So the IHME, that's the Institute for Health Metrics and Evaluation model that I have pictured here. This is a statistical model, and a modeler, a mathematical modeler would call that empirical. So an empirical model, empirical means based on evidence, basically based on observations. And so the way that this model is built is they look at basically lots of different data sources and then use statistics to get an estimate for what might happen in the future. In contrast to an empirical kind of model is what you would call a mechanistic model. And what a mechanistic model does is it actually digs into how the phenomenon in question actually works, right? The mechanisms of action. So for a disease, we're talking about the ways that it's transmitted, the way that it acts on the body potentially, or at least the disease course in the case of a population level model. Um, and it's a very different type of model. An empirical model doesn't really concern itself with questions like that at all. Um, whereas a mechanistic model is really focused on the nuts and bolts of how things work. So there are advantages and disadvantages to both. Um, what I am familiar with and what I do is mechanistic models. So let me briefly talk about what an empirical model might look like, and then we'll get into detail with the mechanistic approach. So as I mentioned, an empirical model is statistical in nature usually. What that means is you're deciding ahead of time what kind of shape you expect the data to have. For lots of good reasons, we expect an epidemiological model to have an S shape. So you can see, and I'm going to try and highlight this. So, oh, yep, I'll bring that back in just a moment. All right, so, well, okay, I can't highlight. Thank you for being here in this fun experiment. If you look at the first figure, the top left there with all the little green curves, the bottom one is what I mean, the S-shaped curve, for many good reasons, which actually a mechanistic approach will illuminate. The trajectory of an epidemic usually follows an S shape. So for instance, if you measure the total number of infections over time, you probably have that nice S or sigmoidal shape. In more morbid, from a more morbid perspective, also the number of deaths in an epidemic is usually S-shaped. So you have an initial portion where it starts very small and starts to grow quickly. And then toward the end of the epidemic, then it levels off again. And so what the IHME model does specifically, and what empirical models often do in general, is sort of choose ahead of time a general shape that they think the epidemic's going to take. So in the case of the IHME model, that shape, it follows what's called the standard Gaussian error function, which I've drawn in orange there. The very complicated looking equation there, that's taken directly from the IHME model, but that's nothing more than the standard Gaussian error that gives you that sigmoid shape. So it looks very complicated, but all it means really is an S. So they assume ahead of time that the total infections over time is going to have that S shape. And then they look at whatever data they have available, and there's lots of data from lots of different sources, including other countries, including other states that are further along in their outbreaks than, say, Minnesota is. And even looking at past epidemics as well, for instance, the Spanish flu back in 1918. And they can get statistical samples of the kinds of things that governments and people did in response to those outbreaks and how they affected the curve. And using complicated statistical magic, they come up with a curve that comes closest to fitting the data that they think is most likely what's going to happen in the future. But it's statistical in nature, and it's not possible to answer some questions with a model like this. Questions like, which specific things that we're doing are affecting the model more or less? And since it assumes ahead of time what shape the epidemic's going to have, it could be definitely a limited approach if, well, if an epidemic for some reason doesn't have that shape. Right, so that's one type of model that you may have seen. The type of model that I'm familiar with, and the type of model that the University of Minnesota, in conjunction with the state of Minnesota, is using, is a mechanistic one. So I'm sorry, I hear my dog at the door downstairs. I may have to go let my dog in. I'm very sorry if I do. So a mechanistic model, what you do in one of these is you pick some things that you want to keep track of. We'll call those the variables. Those are just things that change over time. So you're going to see those are things like the number of people who are infected. You want to describe how they're related to one another. So in an epidemic, of course, the number of infections is related to the number of interactions you have between people who are infectious and people who are susceptible to that infection. And then you describe somehow how those relationships are modified by various environmental factors. You call those parameters. So examples of parameters would be things like how often people are going out of their house, how often they're washing their hands, things like how much hospital capacity you have are all parameters. All right, so advantages of a mechanistic model is that you can interpret the results really easily because usually that's how we're thinking about how an epidemic works anyway. When you have a mechanistic model, it usually matches our intuition for what's going on. It also matches the way that scientists who are actually doing experiments think about systems, which is really good because it allows you to do things that an experimentalist can't do but maybe would like to. You can do experiments by changing some of those parameters. Say, suppose we had a stay-at-home order and didn't let people interact as much. How would that affect the epidemic? And that's a really, really powerful tool that mechanistic models gives you. And it's one of the reasons that they're relied on so heavily for making policy decisions. Of course, there are disadvantages of mechanistic models as well. Because you're keeping track of so many little details about everything that's going on, often you need a lot of data to be sure that you have a good model. It's also, of course, you still have to describe those relationships. And so if the modeler doesn't have a good handle on what those relationships actually are, then they're going to make potentially a bad model, potentially a misleading model. So it's really important to, as a modeler, keep those things in mind, use your best judgment, but always be open to revision when appropriate. All right, so empirical models versus mechanistic models. And we're going to focus on mechanistic models. All right, specifically, the type of mechanistic model that we're talking about today is called an SIR model. So each letter stands for a different class of people, a different compartment of people. S stands for susceptible, meaning you are able to be infected. I stands for infectious. In some cases, it actually stands for infected. An infectious person is someone who has the disease and is able to pass it along, to transmit it to someone who's susceptible. And R stands for removed. So you could think of R as sort of standing for recovered. In cases where you have absolutely no behavior change, then it would be recovered. Removed means the person is no longer interacting in a way that could transmit the disease. So you can imagine lots of ways to become removed. You could recover from the disease. You could also self-quarantine or go to the hospital, or in worst case scenario, you could die. So there's lots of ways to stop interacting as an infectious person. And we just group all those into the R class. Okay, so the most basic types of models, and the one that I'm going to go into detail in just a little bit, only has those three, S, I, and R. But actually, for most diseases, you often want more than those. So really common are exposed classes. This is something that we see is really important for COVID-19 because from the moment that you have that interaction that gives you the infection until you actually become infectious can be quite long. It can be as much as, on average, 5 or 6 days for this particular disease. And so it's important to capture that delay in the model. So you might want to add an exposed class. For some diseases, you could be a carrier where you have the either maybe the parasite or you're carrying a gene or something, but not affected yourself. You could be asymptomatic, so you could be infectious but not have any symptoms. Sometimes you actually want to explicitly include hospitalizations or quarantines in the model, and so on. There are diseases like malaria or dengue that are actually very complicated diseases that are passed from vectors like mosquitoes. Chagas disease is transmitted from kissing bugs. And so often a model will even have compartments for bugs or livestock or other groups of individuals who could carry the disease. You might have a disease that has several stages of action, right? So you might have more than one infectious category, corresponding maybe to mild, severe, maybe different classes of symptoms or different levels of infectivity. The point is, the SIR framework is really, really flexible. Given whatever disease you're looking at, you sort of figure out which compartments you think might be important. You can write down a model very quickly for how those compartments interact and kind of iterate on that. It's very nice. You can also add age structures or genetic structures or ethnic structures or structures based on someone's history of disease. For instance, if you're looking at shingles and chickenpox, that would be really important. So it's just a really flexible approach. All right. There's no questions yet, which really worries me because I know I'm going too fast. So please feel free to throw some questions in that Q&A. All right. So we have mechanistic models. There are more than one approach, of course, to mechanistic models. The first, and what I don't do, is called an agent-based model. So an agent-based model, the agent here is the individual. You follow every person in the population, and you sort of say, well, you assign them one of those states, right? So S, I, or R, depending on whether they're still susceptible, or currently infectious, or removed from the infectious population, or any of the other states that you think might be important for your disease. So each individual is their own variable. So for instance, if you're talking about Minnesota, you'd have more than 5 million variables because there's more than 5 million individuals in the state. You then have parameters that describe how those individuals behave. So you might have, in the extreme case, every individual has their own tendency to go out and interact, right? You can keep track of who interacts with whom. You can keep track of things like grocery stores, where certain people tend to interact with each other a lot. And you can get really interesting and very detailed models set up with an agent-based approach. And they can be really enlightening because they match really, really closely with how we think about epidemic spreading, right? We think about people interacting with one another. And rather than try and illustrate this myself, I want to show you something that the Washington Post put together recently. Oh, you can see all my tabs. No, that won't do. Let's just look at that tab. Okay. So here is an illustration. This is an agent-based model of a disease spread, where you have every individual in this small population represented by a dot, and the color of the dot represents their state. So they're either susceptible, infectious, or recovered. Everyone starts susceptible, that's light blue, except for one person who starts infectious, that's orange. And then over time, when you're infectious, slowly you fade to pink, meaning you're removed. So I'm going to play that again, and you can see right in the middle is where that first infection starts. And then these people, these dots are bouncing around kind of randomly. And of course, you don't have to make it random. You can have them going on paths, going to work, going to a grocery store, or what have you. And then see how things evolve. it's a really enlightening way to think about what's going on. I want to point out this graph here right above the animation too. This is showing the number of people over time, or actually the proportion of people in each class over time. So you see you start with all blue, meaning all susceptible, and the number of infectious individuals increases over time, plateaus, and decreases. And the number of recovereds then follows that nice S shape as well. And so agent-based models can be great because you can be really detailed, like in this one where they simulate a unsuccessful quarantine by having these bars blocking the little balls a little bit. And you see what happens is the curves are a little different. And you actually get this really long, flat plateau as the quarantine sort of stops working, stops being super effective. You can do all sorts of fun stuff with an agent-based model and get really cool insights. Here they're having some individuals not move at all to represent social distancing or isolation. Right, so these are some great illustrations of agent-based models. And so as you can see, they're pretty powerful, they're pretty useful. They have disadvantages, which is if you have 5 million variables and you have, say, a dozen parameters for each individual, then it's extremely complicated. It can be hard to interpret the results you get when the results are just that graph, because they're based on all these many different things happening, and it's just not possible to keep track of all that. And there are mathematical tools for working with agent-based models, but just because of the complexity, it can be really hard to really say anything conclusive about them. You're often limited to making statistical arguments like, most of the time in our model, this happened. What's really nice for a mathematician is to be able to prove things, to say, for sure, in this kind of model, this is what happens. So we have our first question, and the question is, are all states using the same mechanistic modeling approach that Minnesota is? To be honest with you, I don't know. I would guess that it's all pretty similar. I just about guarantee that they're all using SIR frameworks. Some of them, I'm sure, are using a combination of approaches. I know that the IHME model, which is purely statistical, is also being used to help set policy in a lot of places. Yeah, so we have a second question, which is about immunity. So in this very simple case where we have just S, I, and R, if you're in the removed class, in particular, you can't be reinfected. Of course, that's not true for all diseases. For instance, the common cold, you can get again and again and again. You don't become immune to it. There's lots of diseases that you don't become immune to. On the other hand, there are lots of diseases that you do become immune to. And so building the model based on that information is really important. So the question is, how do you change the model to include that? And the answer is, I'm going to have some nice pictures in about 2 slides that I will show you exactly how to do that. But that'll have to wait for a couple minutes. So if I forget to circle back to that, just shout. All right, so an agent-based model follows everyone, and it's complicated and beautiful and not what most people do. What most people do is use population-based models. Okay, so in a population-based model, your variables are the number of people in each compartment, in each class. So if you just have S, I, and R for your classes, then you have 3 variables. And then the parameters describe how people move between the classes, right? So we know that people move from S to I when they become infected, and they move from I to R when they either isolate or recover. And possibly they move back from R to S if they don't have immunity, or if they have limited immunity. So advantages population-based models, you can probably guess based on the disadvantages of the previous models. which is they're easy to understand, they're easy to interpret. Mathematically, they're tractable, so we can prove things about them. We can reduce very complicated questions to what are relatively simple mathematical ideas that we can understand and act on. The disadvantage for a population-based model is that you're thinking about an entire population. And if your entire population has a lot of differences, if it's very heterogeneous, if you have, say, a big mix of very urban, densely packed, lots of interaction people, and rural, not dense, lower interactions people, then your model, if you're including both of those populations in your model, isn't going to be exactly correct for either of those subpopulations. So it's really important when you do a population-based model to think carefully about who your population is and whether or not it makes sense to sort of take an average over them. Let's see, so we have another question. So the question is, in Minnesota, are we using multi-modeling approaches? So to be honest with you, I don't know. I don't know exactly how the governor and the Department of Public Health are making their decisions. I do know, so I can show you this paper. So the Minnesota Department of Public Health and the U of M School of Public Health are partnering on one particular model, which is very much like what I've just showed you. I don't know if they're using anything else. So we'll come back to this picture here in a minute in particular. I'm sorry, I don't have a better answer for you. All right, let's get into some details now. So we have the SIR framework. We think of people as being susceptible, infectious, or removed. And then how do we actually do that? So I told you we have 3 variables. So we'll let those variables be S, I, and R, appropriately enough. We'll let S be the number of susceptible individuals, I be the number of infectious individuals, and R be the number of removed individuals. We have to make some assumptions. We're going to assume that a typical individual in our population, and typical is a really important word here, right? We're averaging over the whole population. Some people will do more, some will do less. So we're really talking about an average. A typical individual will interact with some number, call it little n, lowercase n, of people, some number of people every day. And then you assume that when they do interact, if the other person happens to have the disease, then there's some probability P of them transmitting the disease to the susceptible individual. And in the simplest model that I'm showing you here, we're going to assume that someone who's infectious doesn't change their behavior. They're just going to interact with the population in general, but leaves the infectious class for one reason or another after some number of days, which we'll call little r. One of the great things about SIR models is that you can capture just about everything there is to know about the model by drawing boxes and arrows. That's what I've done here. We have a box with an S in it, a box with an I in it, and a box with an R in it. There's an arrow going from S to I and an arrow going from I to R. So in the model, as I've set it up here, individuals can only move in one direction, right? Over time, you see, and we'll reflect this in some equations in a minute, but over time, you see that the number of susceptibles can only go down because there's no way to enter that box. You can only leave it. If you want to include in the model the possibility that people could get reinfected, there's a really easy way to do that. Hopefully this will update in real time. Yes, you add an arrow from R to S. So that's called a waning immunity model. And it has really important implications for the disease that we won't have time to talk about right now. unless y'all are really into it. But for now, let's assume this simple model. You can draw arrows all over the place, but notice also that I've labeled the arrows with rates. So the rate of movement from S to I is P times N. That's the probability of infection per interaction times the number of interactions, times S, so that's the number of susceptible people. That's the total number of interactions that might lead to infections. And times I over N, which is the proportion of the population who's infectious. In other words, it's the probability of meeting an infectious person. We also have movement from I to R, and that moves at rate I divided by R. And I got ahead of myself there because I've explained what those mean on this slide. So I over N is the probability, if you're interacting with everyone randomly, and that's a very important assumption that this kind of model makes. That's the population assumption, that it's a heterogeneous population. So if you assume that you're interacting with people more or less randomly, then the probability of interacting with an infectious person is just I over N, the proportion of individuals who are infectious. Okay, if it takes R days to recover or to remove, then on average, 1 over R, the fraction 1 over R of all the infectious people are going to be entering the removed class each day. So if it takes 5 days, then on average, 1/5 of the people are going to leave each day. So that over those 5 days, everyone leaves basically. All right, so that's where those labels come from. And then what you do once you have the boxes and arrows and the labels on them, you can write down equations that describe how the variables change. So we're going to let S of t, so the t means time. So S of t is the number of susceptibles at time t. So S of 0 is the number of susceptibles at the very beginning. That's going to be everybody probably. And S of a billion is going to be however many people never got the disease in the first place. And in between there, for different values of t, after 1 day, after 2 days, S of t will tell you how many people are susceptible on that day. Same thing for I and R. And then mathematical shorthand for talking about rates of change of variables, you just add an apostrophe there, or we would call that a prime. So when we write S prime of t, that just means how S is changing. And I prime of t is how I is changing, and so on. Everything here is representing numbers. So S prime of t is going to be a number. It's going to be a number described by some of these parameters, right? So here's the equation. But if that number happens to be positive, then that means S is increasing. And if that number is negative, then that means S is decreasing. And it's the same for all 3 variables. So truly, all I've done is taken the labels from the arrows and put them in the equations with either a negative sign or not. So there's a negative sign if you're leaving, right? So S prime, that's how S is changing. S is decreasing. And S is decreasing at this rate. So we'll write S prime is negative A times all this stuff. So we have a question. The question is, why is I being divided by N? So there's 2 answers I could give to that. One answer is because it makes everything a little better. It makes the number A something that we can understand intuitively. But the second answer I can give, and probably the better answer, is that you can think of this rate, the A times S times I over N, as the number of new infections in a day. So I over N is the probability that any particular interaction is with an infectious person. When we do the S times I, we're making, like I said, an assumption that the population is homogeneous, that everyone is sort of interacting randomly with everyone else around them. And it's actually a tool borrowed from chemistry. It's called mass action. or if you have two different chemicals that are going to react and they're floating around in a solution, then the rate of that reaction is just proportional to the product of their concentrations. So we're also kind of thinking of people as chemicals who react. And when they react, you get a new infection. But really the best answer is just think of I over N as a proportion. I over N is the fraction of people who are infectious. And that's the probability that you meet an infectious person. All right, so we've got these three equations that talk about how the variables are changing. And you see S prime, S is changing, it's always negative. You have negative times that term. It can only decrease because the arrow only leaves. If we added that arrow going back, oh, I'm on a different slide here. If we added that arrow going back, hopefully that updates relatively quickly. It's very hit or miss. Yeah, there we go. So if we added that arrow, then we could add down here to the equation another term as well, a plus some amount. And we'd then have a corresponding minus some amount from the R prime equation. So each arrow is one of the terms in the equations. That's the main story here. Each arrow gives you one term, and it's going to be positive if the arrow points into that box, and it's going to be negative if the arrow points out of the box. So again, really intuitive to set up and to think about what shape your model should have. All right, so we have these equations. And of course, what are we interested in as epidemic modelers? Well, we're interested in usually controlling the epidemic, in getting to a place where the number of infections is decreasing rather than increasing. And so a really natural question that you can ask for a model like this is, under what circumstances will I increase or decrease? So to answer that question, we'll just look at that equation, at the I prime equation that tells us how it's changing, right? And if it's positive, if that stuff over here to the right is positive, it's going to be increasing. And if it's negative, it's going to be decreasing. And here we have one thing minus another thing. And so we know that'll be positive if the first thing is bigger than the second. So if A times S times I over N is bigger than B times I, then the number of infections will increase. If A times S times I over N is less than B times I, then the number of infections will decrease. So you may remember algebra however long ago. We have the same thing on both sides of the equation, so we can cancel it, get rid of those i's. I'm also going to divide by A. So I have S of t over N on this side. On this side, I have B over A. And so we see that the number of infections will increase if the number of susceptibles, or actually the proportion of the population who's susceptible, is larger than this ratio, B over A. Now remember, B is the rate of removal from the population, and A is the rate of new infections. So what we're saying here is we need people leaving the I class faster than they're coming in. And if you have more people leaving than they're coming in on any given day, then the total number is going to go down. Right? So we need, okay, we want I to be decreasing. So we want the second thing to be true. We want S over N to be less than B over A. There's two ways to make that happen, right? If you want one number to be less than another number, then you either decrease the first number or increase the second number. So we have two ways to get about this. We want to either decrease S or we want to increase B over A. Okay, decreasing S is what's called herd immunity. So you may have heard about herd immunity. Herd immunity is the idea that there just aren't that many susceptible individuals, so that if there's an outbreak, it just won't be able to take hold. There won't be enough people to spread to, and you'll never have an epidemic develop. herd immunity is usually achieved through vaccination. For instance, chickenpox, polio, measles, all sorts of diseases that we think of as things of the past got that way because we implemented vaccination strategies. Vaccination removes people from the susceptible class, puts them in R right at the very beginning, rather than forcing them to go through I on the way there. The other way to decrease S, of course, is to have people go through I, right? Is to actually have lots of people become infected. This only works, and so this was a great question earlier. This only works when the disease grants immunity upon recovery. It's very important to know for sure that a disease is going to do that before you try and take this approach. Unfortunately, at the beginning of an epidemic, data is scarce, and it's often not possible to know answers to questions like, will I be immune after recovering from this disease? So that's strategy one, is decrease S. And the best way to do that is with vaccines. Until you have a vaccine, decreasing S isn't really an option. So strategy two, increase that ratio, B over A. So this is what we're doing when we're doing things like social distancing, practicing hand washing and mask wearing, and taking care to do lots of testing and tracing. So B, remember, is the rate of removal from the infectious population. So if B is large, that means people are self-isolating quickly or being isolated. They're finding out that they may be infectious before they have symptoms, right? And so they can leave I much more quickly. The bottom of that fraction is A, and of course, to make a fraction bigger, you want to make the denominator smaller. And A is the rate of new infections. So of course, if we can make the rate of new infections smaller, then we'll increase that ratio. How do you make the number of new infections smaller? Well, you either decrease the number of interactions people are having. It's making N smaller through social distancing, staying at home, and so on. Or, and hopefully also, you decrease the probability that any of those interactions actually leads to a new infection. And that's why masks and hand washing, sanitation, and so on are so important as well. So what's really great about this model, like I said earlier, is you can really understand it. You can understand what the model is saying very intuitively in terms of the real world, in terms of what we're doing in real life. Yeah. All right, so strategy two would be my choice if you're asking. All right, something else you may have heard of, so you've probably heard about herd immunity. If you're following the news, you're probably also hearing about the basic reproduction number, sometimes pronounced R naught. British people call 0 naught. I call it R0, you can call it R naught, or just the basic reproduction number. The basic reproduction number is the average number of new infections that will be created by someone who's infectious now. So here's a nice, this picture here is kind of a nice explainer. If R0 is 2, if your basic reproduction number is 2, that means each person who gets the disease is on average going to infect 2 other people. So each generation of the disease then, the total number of people who are infected is going to be almost doubling. Of course, people will be recovering as well, but it's going to be growing pretty fast. If R0 is 1, then that means the total number of infections should actually be staying constant. Because for each person who gets the disease, they're going to infect exactly 1 person who replaces them. So R0 equals 1 is the break-even point. What you want is R0 to be less than 1. That means on average, people are infecting fewer than 1 person, and the total number of infections decreases over time. So that's your goal. That's your public health goal. In terms of the model that we've set up, we can actually say exactly what R0 is. This is another really great advantage of this type of model, it's equal to S divided by N times A over B. It's great. It's the exact same parameters we were talking about. If A over B is greater than 1, at the beginning of the outbreak, S is going to be almost exactly N. So S over N is going to be almost exactly 1. So at the beginning of an outbreak, you need alpha to be smaller than, sorry, A to be smaller than B. That's what you want. You want fewer new infections than you have people leaving, right? More out than in means overall decrease. All right, so that's R0. So herd immunity and the basic reproduction number, that's what those are. There's one last thing I wanted to mention. Oh, sorry. What do we get when we write down these equations? So one of the advantages of these equations is you can solve them really quickly. So this took a fraction of a second to draw these pictures on my computer. This is exactly solutions to the equations I just showed you. So we're starting with, in this case, this actually is 5 million people. Totally irrelevant though. And I chose values for A and B that are just kind of nice and illustrative. So in this first picture, A is 0.3, B is 0.1. The susceptible population is shown in blue. So you can see at the beginning, at time 0, everyone is susceptible, or nearly everyone. Over time, the number of infectious individuals grows to its peak and then decreases. And then the number of removed people is green, and that grows and eventually levels off. So in the first picture, I have A is 0.3 and B is 0.1, meaning people are being removed from the population in about 10 days. So that would be basically following the normal course of the disease in a lot of cases. In the second picture, I decreased A to 0.26, which would correspond to changing the number of interactions very modestly, right? This is something like a 15% decrease in the number of interactions you're having. And I changed B, I increased B to 0.14, meaning people are now leaving in about 7 days. In the third picture, I decreased A to 0.22, which is something like a 40% decrease in the number of interactions you're having from the first scenario. And I increased B to 0.18, meaning people are isolating or otherwise entering the removed class in about 5 days. You see there's a dramatic difference in the number of infections that occur. Small changes in these parameters can have a huge effect on the course that an epidemic follows, at least in this kind of model. And I have to emphasize that it is a model. It's also worth saying that these models do match very closely with what has happened in real epidemics in the past. All right. Excuse me. Okay. We have another question, and it's a perfect question for this moment. So the question is, how do we get R0? How do we get that basic reproduction number? And the answer is, well, we kind of guess. The process is called parameter fitting. And the idea is we have these parameters. We have A and we have B in the model. And if we know what A and B are, then we know how to calculate R0. So if we know what A and B are, then we know what R0 is. But do we know what A and B are, and how can we know what A and B are? That's our goal. Oh my goodness, I'm talking a lot. I'm sorry, I'm a talker. Well, if you can, you measure the parameters. You go out there, you keep track of how long people are sick for, how many interactions they're having in a day, and so on. Often that's really difficult, especially at the beginning of an epidemic. So strategy 2 is curve fitting. What you do in curve fitting is you basically try getting outputs like what I just showed you. You run the model a bunch of different times, millions of times with different parameter values. And you just see which combination of parameter values gives you output that's closest to what you're actually seeing. And that process is called parameter fitting. And finally, the last thing that we need to talk about is uncertainty. All models are wrong. This is the first thing we talk about when we teach a modeling class. We say all models are wrong, and all parameters are estimates. And it's really important to know that. But if you do keep that in mind, it's totally possible to come up with really valuable results that can still be really, really useful. There's a whole process for doing this called sensitivity analysis. Because I've been talking for so long, I'm going to just kind of glide over this. But the idea is there's ways to measure that uncertainty. And so what you'll often see in model predictions like the IHME model is an envelope like what I've got pictured in the bottom right. So you have the predicted curve, that's the best fit. That's what the parameter fitting tells you is probably true. But then you do also a measurement of how wrong might you be. And then you get often what's called a 95% confidence interval. It says, well, we'd expect if we made the same prediction in 20 different epidemics, 19 times out of 20, it would be somewhere between these two extremes. So we're allowing for the possibility that we're wrong. We're sort of allowing for how wrong we might be, and then keeping that in mind, you can still make informed decisions. And so that's how models are used in the real world. It still involves human judgment at the end of the story. Okay, I've just been talking at you. I am very sorry. This is supposed to be interactive. I'd like to invite all of you out there. I'm going to open up the chat. Let me see. So we have a new question. If a disease is sometimes fatal and sometimes not, is it a problem that R0 or the R that the removed class includes both deaths and recoveries? From a public health point of view, isn't it important to distinguish those cases? Yes, 100% it's important to distinguish those cases. That is a nice segue to the U of M model. So here is the box and arrow plot. They didn't draw boxes, they just put letters out there. Here's the box and arrow plot for the U of M model. And you see they have a D. They are explicitly modeling the number of people who are dead. It can be tough to talk about. I try not to talk about it too much, especially in a public setting. But yeah, it's absolutely important to make that distinction in most real world models. While I have this open, I guess I'll show you the equations. So they have, where are they? 9 equations. They're in here somewhere. Let me just keep scrolling. I'm going to find them. I've seen them. I saw them just now. There they are. So these are the 9 equations explaining how each of those boxes changes over time. You can see it's somewhat complicated, but not tremendously so, right? Each equation just has 1 or 2 terms, right? People entering that state and people leaving the state. So although what I showed you, can I maximize? Yes, of course. So although what I showed you is a simplification, it's actually not that far off from the kinds of models that people are really using. It's really pretty straightforward. People coming in, people going out of each box. All right, have we got any other questions? Do I think this model is appropriate for COVID-19, or would I modify it? That's such a great question that I don't want to answer. Excuse me. As I mentioned, I'm not actually an epidemiologist. So my understanding of this is really limited to sort of the mathematics of it, the considerations of it when you're doing a model. But I'm not an expert on COVID-19 in particular. So it's hard for me to say exactly. I think one of the goals of the UMN model um, was to think about ICU capacity, to think about healthcare capacity, and was trying to make decisions in that light. And so, for instance, having an ICU class here definitely makes sense, right? You want to keep track of how many people actually need that healthcare. I will mention in the model that I built with my class, we did include two different infectious compartments. We had a pre-symptomatic and a symptomatic compartment. Because from what I've read from WHO and CDC, seem to suggest that there's actually quite a bit of transmission that's happening by people who don't yet know they're sick. And so thinking about the relative importance of controlling asymptomatic transmission versus symptomatic transmission might be something really important as well as you're thinking about public health strategies. I've seen models that explicitly include testing. Right? One of the issues that we're having right now is a lack of data. And so there are models that will have a class of infectious people who have not been tested and a class of infectious people who have been tested. And what that does is it helps you use the data that we do have when you're on that parameter fitting step. So those are two changes you could make to this model, but the model choice and the model structure is really closely tied up with the questions you want to answer. And I think for this group, the question they wanted to answer was, how do we keep our healthcare system from being overwhelmed? And so I think this is probably a very good model for that. Well, let me thank you all again for being part of our inaugural Cafe Sci webinar series. Um, it's really great to see so many people who are still interested in staying engaged. And I really appreciate having the ability to share what I know a little bit too. I'd like to make myself available outside of this. So please feel free to contact me. So I'm going to put my contact information in the chat. My email address is buckalew@d.umn.edu. That's my University of Minnesota Duluth account. If you have any further questions, feel free to contact me. We will upload these, my presentation materials. We'll put those probably, I think, on the Facebook page or on the Cafe Sci website as well. So feel free to follow up. Thank you. Thank you for attending. Yeah. Yeah, calculus isn't scary. It doesn't need to be anyway. Okay, my dog is really angry that I've left her outside this whole time. So I have to get going. Thanks again, everybody, and stay safe and stay healthy. We'll see you hopefully next month.